Hello, I am Zahra Ibrahimi, a research associate from the Chair of Processor Design at TU Dresden in Germany, and I'm glad to present to you our paper SIMDive, which is an approximate SIMD hybrid multiplier divider for FPGAs with tunable accuracy. So the main concern for the designer of modern applications like machine learning and big data is to gain high performance within a limited power budget. The common feature of these programs is their tolerance toward errors in their computations. So to address these challenges, the concept of approximate computing has came into the picture, which can improve performance metrics in exchange of some tolerable errors. Another point that can improve especially the throughput and energy efficiency is the concept of SIMD, or single instruction multiple data. And it perfectly suits these applications as the required precision varies not only among them, but also within each one. For example, different layers of a neural network require different bit widths. But what functions are suited for approximation? While most of works have concentrated on adders and most importantly multipliers, still division exists in such applications, and this operation acts as the frequency bottleneck. So both multiplication and division functions are hot candidates for approximation. Here is a summary of the state of the art with respect to SIMD and approximation. First category summarizes approximate multipliers, none of which could support division, while also their reported gains are limited in FPGAs. Second category targets approximation of division. The main issue here is that an SIMD version of accurate division is not mathematically feasible. Moreover, none of the previous dividers have been efficiently merged with a multiplier. It should be mentioned that division latency is very high, especially in FPGA it is more than 3 times of a multiplier latency. The works in the third category, while targeting SIMD design, they only implemented multiplication and the resource gain were not significant. So we have proposed our SIMDive approach that can intelligently address all of these challenges by offering the first hybrid multiplier divider, which also supports both variability of bit widths and accuracy. But how we designed SIMDive as the first hybrid multiplier divider? We have used Mitchell's algorithm. It translates multiplication into addition and division into subtraction in the logarithmic representation. But the error for this algorithm is high, around 4%. So we have reduced this error to less than 0.8%, while still significantly gain in terms of throughput, area, and energy efficiency over accurate version. We made it SIMD with a low overhead. The very interesting point is that this SIMD mode with hybrid functionality offers significant improvement over a single 32-bit multiplier or a divider. We have also evaluated SIMDive in 3 image processing and neural network applications. I briefly explain Mitchell's algorithm here with an example. When the log is applied on the multiplication, it is transformed to an addition. So the first step of Mitchell's algorithm is finding the log of the inputs, which would be approximate in his algorithm. The log is calculated in this way. In the binary representation of the number, the position of leading one is detected and considered as the integer part, and the rest of the bits are considered as fractional part. And the sum of these two parts make the approximate log. In the second step, both integer and fractional parts are added separately. Finally, to apply the approximate antilog and get the result of the multiplication, 1 is appended to the summation of the fractional parts, and then it is scaled with respect to the sum of the integer parts. Interestingly, when additions are changed to subtraction, this algorithm implements an approximate division as well. This is the overall structure of our SIMDive. Part A shows the overall 32-bit SIMD mode in an abstract way. For example, when precision is changing from 8 to 16-bit, the carryout from the first 8-bit adder should be connected to the carry-in of the second adder to provide the 16-bit addition required for our Mitchell-based multiplier. Part B shows how 8-bit hybrid functionality works. The main difference of multiplication division in Mitchell's algorithm is that the second operand should become negative. So we take care of this with the 2's complement module as can be seen in this figure. We also add the error reduction terms here with the minimal overhead, as I will discuss it more later. To propose our accuracy configurable scheme, we have analyzed the error of Mitchell's algorithm and found some interesting points. First, as you can see in the figures, the magnitude of error depends on the size of multiplier or divider. But within each of power of 2, the error repeats the same behavior in each of multiplication or division. In other words, referring to these equations, the behavior of error does not depend on the multiplier or divider size, but only on the fractional part of the numbers, which are the bits start at the position of leading one. This means if we provide a unique reduction scheme for each power of 2, we can use it for different sizes of multipliers or dividers. As mentioned, the error depends only on the fractional parts. So we came up with a very interesting error reduction scheme that can perfectly fit into the structure of LUTs. First, we divided the squarish region between power of 2's to 64 subregions based on 3 MSPs of each of fractional parts. But why 3 MSPs? Because we had in mind to customize our scheme to 6 input LUTs. Nonetheless, our scheme is scalable to arbitrary size of LUTs and can further improve error. Then we calculated each of 64 coefficients based on original Mitchell's error for each region as shown in this formula. Now consider the binary representation of these coefficients. Each of these green columns represent 64 values of one specific bit position in 64 coefficients. This means each column can be represented by a distinct 6-input function based on 3 MSPs of fractional parts. So a 6-input LUT can calculate the function of one column, or you can say one bit in each of 64 error coefficients. This interestingly shows by adding only one more LUT at the end of this chain, the accuracy of error coefficients can be increased by 1 bit. As I mentioned, we have proposed our error scheme in such a way to also minimize the overhead of adding it to the main circuit. The coefficients are calculated based on fractional parts, so they can be added directly to them and then become scaled. This would avoid using an extra shifter. And even more interesting point is that we also don't use any additional adder to add it to the main Mitchell's multiplier. But how? Let's how it's done in the left figure. And a slice of FPGAs consists of 4 LUTs with a carry chain. Altogether can implement a binary adder. An interesting point is that these LUTs can be configured also in such a way to implement a ternary adder without extra overhead. So we use this concept to add our error coefficients. Here's our experimental setup. We have used Vivado 17.4 and its power analyzer and simulated all designs on vertex 7. We reported area and peak throughput, and for power and energy estimations, we used 100 million random inputs. We also performed exhaustive accuracy analysis for all designs and reported average relative error and peak relative error. The results are shown here. To summarize, we can see the error of our SIMDive is bounded to 0.8% for both multiplier and divider, and it is independent from the operand size as discussed before. The latency of SIMDive divider is 4 times smaller than the accurate Linux IP. In SISD mode, our hybrid multiplier divider is even smaller than an accurate multiplier. And in SIMD mode, not only smaller than an accurate multiplier, but also has up to 37 times higher throughput than an accurate divider. Finally, in terms of a cost function we took from the literature for an overall estimation, SIMDive wins over other designs. We also evaluated SIMDive by porting it in high-level applications. We have implemented 2 image processing applications, namely image blending and Gaussian noise removal filter, with accurate and approximate multipliers and dividers. In both applications, not only the PSNR of our hybrid multiplier dividers is better than the state of the art, but also it is highly attractive in terms of resource, as it obviates the need of separate multipliers and dividers, where the latter could limit the overall speed of the circuit. In addition, we have evaluated our SIMDive in the inference phase of a neural network for classifying MNIST and fashion handwritten digits. We trained the network with accurate multiplier, double precision floating point, and then replaced the accurate multipliers with our 8-bit SIMDive version for the inference phase. As you can see, due to the resilient nature of the neural network, most of error has been masked. Interestingly, our SIMDive not only can achieve same or even higher accuracy than accurate network, but also it gains in terms of resources. So in conclusion, we propose the first design methodology for approximate hybrid multiplier-divider, both SISD and SIMD mode. SIMDive is a small scale, highly energy efficient with high throughput when compared with accurate versions and state-of-the-art. Our error reduction approach is easily scalable and independent from the operand size. And for the future tracks, we have started to explore the efficiency of SIMDive when being deployed in soft processors like RISC-V. We also would explore using Approximate adders for LSB additions of the fractional parts. These are the main references discussed in this presentation, and I would like to thank you a lot for your attention.